Ask a physicist what time is and watch what happens. Not what they say. What happens in the pause before they say it. That pause is the subject of tonight's exploration, because there is something strange sitting at the center of modern physics. Something so basic that most people never think to question it, and so unresolved that the people who study it for a living have spent the last century circling it, without ever landing. The question is simple enough that a child could ask it. What is time? Try answering it yourself, out loud, without using the word time or any of its relatives. No saying it flows. No saying it passes. No saying it ticks. Just describe the thing itself, the raw substance of it, the way you might describe the taste of salt. It is the first sign of something deeper, because for 3,000 years, the smartest humans who ever lived have tried to answer this question, and the honest record of their attempts looks less like a march of progress and more like a loop. Start in Athens, roughly 2,300 years before the modern era. A philosopher named Aristotle sits down to write the fourth book of his treatise called Physics, and he offers a definition that still gets quoted in classrooms today. Time, he says, is the measure of motion. It sounds clean. It sounds almost too easy. Something moves, you count how long it takes to get from one place to another, and that count is time. A shadow crawls across a sundial. A heart beats. You tally the beats, and you call the tally time. For over 2,000 years, that was good enough. Nobody pushed on it very hard, because it matched the way time actually feels. Things move, and the moving takes time. And the two ideas seemed to support each other nicely. Then, in the year 1905, a 26-year-old patent clerk working in Bern, Switzerland, published a paper that quietly broke Aristotle's definition in half. His name was Albert Einstein, and the paper introduced what would later be called the special theory of relativity. Buried inside it was a discovery that motion and time are not separate quantities that happen to interact. They are tangled together at the root. The faster an object moves, the slower time passes for that object, relative to something that stayed still. Move fast enough, and your wristwatch will tick noticeably behind a wristwatch left on a shelf. Time depends on motion. Here is where the trouble starts. Motion, in the most basic physics sense, is distance divided by time. So motion depends on time, and time, according to Einstein, depends on motion. Put those two sentences next to each other and you are standing inside a circle. Aristotle said time is measured by motion. Einstein proved that motion is measured by time. The definition points back at the word it was supposed to explain, the way a dictionary entry sometimes uses the word it is defining inside its own explanation. You flip to the next page hoping for clarity, and the next page sends you back to the first. 2,300 years separate Aristotle from Einstein. In that gap, entire empires rose and fell. Continents were charted. The atom was split open. And the definition of time, run through the two greatest minds that gap ever produced, ended exactly where it started. Circular dot, maybe that is unfair to ask of ancient philosophy and pin the same failure on modern physics. Surely, in the century since Einstein, someone found solid ground. Consider John Archibald Wheeler. If you do not know the name, you know the phrase he coined, black hole. He trained Richard Feynman as a doctoral student. He worked on the earliest nuclear reactor designs. He co-wrote the textbook that a generation of physicists learned general relativity from. If any single human being in the 20th century had earned the right to answer the question of what time is, it was Wheeler. Here is his answer, offered more than once over his long career. Time is what keeps everything from happening at once. That is not a definition. It is a punchline. A man who spent 50 years at the absolute center of theoretical physics, who could describe the curvature of space-time with total mathematical precision, was asked the simplest possible question about the thing his equations described, and he answered with a joke. Now travel backward again, past Aristotle, past Einstein, past Wheeler, to a theologian working in Roman North Africa around the year His name was Augustine of Hippo, and in the middle of a long searching book about memory and guilt and faith, he stopped and wrote one of the most quoted lines in the history of philosophy. "What then is time?" he asked. "If nobody asks me, I know what it is. If I wish to explain it to someone who asks, I do not know." A bishop in a toga and a physicist running particle experiments, separated by roughly 1600 years, arrived at the exact same shrug. This is worth sitting with for a moment, because it is not a small thing. This is not a case of science slowly closing a gap in our knowledge, the way we once did not understand germs and then we did. This looks more like a wall. The most rigorous thinkers in human history, working across 16 centuries, with wildly different tools and wildly different questions, keep bumping into the same dead end. Every serious attempt to define time either loops back on itself, collapses into a joke, or ends in an honest confession that the definition simply is not there. Think about what that means for your ordinary life. The thing that separates breakfast from dinner, the thing that separates the person you were at 5 years old from the person reading this sentence. The most basic scaffolding of your entire conscious existence has never been successfully defined by anyone, at any point in recorded history. Not an incomplete definition, not a rough sketch waiting for someone to fill in the details. None. But maybe that is the wrong way to think about the problem. Maybe time is like color. Nobody can explain the redness of red to a person who has never seen it. And yet redness is not mysterious to physics, because physics does not need to explain the feeling of it. Physics just measures the wavelength, roughly 620 nanometers, and that number is enough to do every calculation you need. You do not have to solve the philosophical riddle of what red feels like. You just count, so maybe time works the same way. Maybe the question is not what is time, but how precisely can we count it? And on that front, humanity has done something extraordinary. In the General Conference on Weights and Measures made a decision that quietly redefined the most basic unit of time on the planet. Instead of tying the second to the rotation of the Earth, which turns out to be slightly irregular, they tied it to something far steadier, the internal vibration of a cesium atom. 1 second, by international agreement, is defined as 9,192,631,770 oscillations of a cesium atom as it transitions between two specific energy states. That number looks arbitrary, almost comically precise, but it is not round because nature is not round. It is exact because the atom itself is exact. Every cesium atom in the universe vibrates at that same frequency, whether it is sitting in a laboratory in Colorado or hurtling through space at half the speed of light. The vibration does not drift. It does not age. It does not care about its surroundings. By the 20th, engineers had built something even better. Optical clocks that use strontium atoms instead of cesium, reaching a precision of roughly 1 part in a quintillion, which is a 1 followed by 18 zeros. A clock built to that tolerance could run for the entire age of the universe, something like 13,800,000,000 years, and lose less than a single second along the way. These clocks are so sensitive that lifting one by a single centimeter changes the rate at which it ticks, because gravity is very slightly weaker 1 centimeter higher, and general relativity says weaker gravity means faster time. We have built machines precise enough to detect the bending of time across the width of a human hand. So here is the uncomfortable question, hiding underneath all that precision. What exactly are these machines counting? They are counting oscillations, vibrations of an atom, transitions between energy states. They are not counting time itself, whatever that would even mean. They are counting a physical process, and then we attach the label second to a certain number of those vibrations. The vibrations are real, measurable, and repeatable. The label is ours. We invented it and hung it on the process like a name tag. We have now measured time more precisely than any other quantity in the history of science, and we still cannot tell you what the thing we are measuring actually is. The instrument is close to perfect. The understanding underneath it is missing entirely. We built a ruler capable of resolving distances smaller than a billionth of a second, and we cannot define what a second fundamentally is, only how to count it. Perhaps you are willing to let the definition go. Fine, you might say. Nobody can define time in the abstract. The clocks just count vibrations, and we call it time, and maybe a label is all we ever needed. But surely there is one thing about time that nobody can take away. It moves in a direction. Coffee cools. Eggs crack. But cracked eggs never spontaneously reassemble. You get older, never younger. Yesterday is gone, and tomorrow has not yet arrived. There is an arrow here, a direction you can feel in your bones. And it is the single most reliable feature of your entire lived experience, except when you go looking for that arrow inside the actual equations of physics, it is not there. In 1954, a German physicist named Gerhard Luders proved a result that a year later was extended by the Nobel laureate Wolfgang Pauli. Together, their work produced what is now called the CPT theorem, one of the deepest results in all of theoretical physics. It states that the fundamental laws of physics remain unchanged if you simultaneously reverse three things: electric charge, spatial orientation, and the direction of time. Flip all three, and nothing breaks. Run James Clerk Maxwell's 19th century equations of electromagnetism backward in time, and every solution still works perfectly. Run the Schrödinger equation, the foundation of quantum mechanics, in reverse, and every process plays out just as cleanly as it does forward. Run Einstein's general relativity backward, and a planet orbiting a star looks exactly the same whether you play the film forward or in reverse. Every fundamental law of physics ever discovered treats the forward direction of time and the backward direction of time as mathematically identical. The arrow you feel, the one that turns an egg into an omelette and never turns an omelette back into an egg, does not appear anywhere in the underlying code of physical law. You live your entire life moving in one direction. Every cell in your body ages in that same direction. Every memory you carry points that same way, and the laws governing the individual atoms inside those cells, inside those memories, are completely indifferent to which way time runs. They do not distinguish forward from backward. You do. They do not. So where does the arrow actually come from? if not from the fundamental laws themselves. In 1872, an Austrian physicist named Ludwig Boltzmann found the answer, and the answer is entropy. The word gets translated casually as disorder, but that is a shortcut. What entropy really measures is probability, the sheer number of ways a system can be arranged. Picture a glass of water sitting intact on your kitchen counter. There is exactly one way for that glass to be whole, upright, holding its water. Now knock it off the edge. It shatters. Water sprays everywhere. Shards scatter across the floor in some particular pattern. But there are billions upon billions of different ways. The mess could have landed and still counted as a mess. Boltzmann's insight was almost brutally simple. The universe does not have a preference for disorder. It is not chasing chaos on purpose. It is simply the case that there are overwhelmingly more disordered arrangements than ordered ones. So, if a system is free to change at all, it will almost certainly drift toward one of the countless messy configurations rather than stay in the single tidy one. That drift is the arrow. Coffee cools because there are vastly more ways for heat to spread out evenly than to stay concentrated in one cup. Smoke fills a room because there are vastly more ways for smoke molecules to scatter than to remain clumped near the match. You age because there are vastly more possible states of a body that are worn and broken than states that are young and whole. Boltzmann turned this insight into rigorous mathematics. A result called the H-theorem, proving that entropy increases as time moves forward. For the first time in history, the arrow of time had an actual mechanism behind it, not just a feeling. But Boltzmann did not stop at the surface. He kept following his own logic, the way you might follow a crack in a foundation wall to see how deep it goes. And what he found at the bottom of that crack was not solid ground. It was a hole. If entropy explains the arrow, then the arrow is a consequence of something else, not a law in its own right. A consequence of what? Of the starting conditions. For entropy to increase steadily from a beginning point all the way to now, the universe had to start in a state of extremely low entropy, an almost impossibly ordered, tightly arranged beginning. Everything packed with a precision that has never been explained. But why would the universe begin ordered instead of messy? What law demanded a clean start rather than a chaotic one? Boltzmann spent roughly 3 decades chasing that question. He built an entire field, statistical mechanics, tools that physicists still rely on today. And he never found the answer. Every path led back to the same hole. The low entropy starting condition is assumed, not derived. Simply taken for granted, because without it, none of the rest of the framework works. In 1906, in a hotel room on the coast of Italy, Boltzmann's life ended. The man who gave the arrow of time its equation never found the ground that equation was supposed to be standing on. And that ground is still missing today, for nearly a century after Boltzmann. Physicists mostly walked round the hole rather than staring into it. They used his equations. They taught his version of entropy in every introductory course. They built entire careers on the arrow he had described. But almost nobody looked directly down at the unexplained assumption sitting underneath all of it. Then, in the year 2000, a philosopher of physics named David Albert finally looked down and gave the whole a name. In a book called Time and Chance, he pointed out that the second law of thermodynamics, the law that entropy increases and therefore gives time its direction, only functions if you smuggle in one additional assumption first, that the universe began in a state of extraordinarily low entropy. Albert called this the past hypothesis. It is not something derived from deeper principles. It is an axiom, a rule you must simply accept before the rest of the machinery is allowed to run. Remove it, and the arrow has no starting point. Entropy has no baseline to increase from. Your coffee has no reason to cool rather than spontaneously heat up. So just how likely is that starting condition, really? The mathematical physicist Roger Penrose sat down and calculated it directly. He asked, out of every conceivable way the universe could have begun, what fraction of those possibilities would have entropy low enough to produce the arrow we actually observe? His answer is a number that does not fit inside ordinary human intuition. It is roughly 1 chance in 10, raised to the power of 10, raised to the power of 123. To picture the scale of that, take the number 10 and raise it to the 123rd power, which gives you a number with 123 zeros after it. Now raise 10 to that entire result. The resulting figure has more digits in it than there are particles in the entire observable universe. You could not physically write that number down even if your sheet of paper were the size of the cosmos. That is the improbability of the exact starting condition responsible for your coffee cooling, your memories running in one direction, and your body aging rather than growing younger. The entire arrow of time rests on a coincidence so staggeringly unlikely that the number describing its unlikeliness cannot be written inside the very universe that coincidence supposedly produced, and nobody knows why it happened. No deeper law predicts it. No equation demands it. It simply has to be accepted as a brute fact. But maybe the whole is not actually a whole. Maybe the question itself has been framed wrong from the start. In the year 2004, a Caltech physicist named Sean Carroll, working with researcher Jennifer Chen, published a proposal that turned Boltzmann's entire problem upside down. Instead of assuming the universe began in a state of low entropy, they proposed it began at the opposite extreme, maximum entropy, total equilibrium, a state with no structure, no gradient, and therefore no arrow at all, a state where nothing happens, because there is no meaningful difference between here and there, hot and cold, anything and anything else that does not sound like the beginning of a universe. It sounds like the end of one, and that, according to Carroll and Chen, is exactly the point. In their model, the universe starts at the flat bottom, not at some improbable ordered peak. From that flat, featureless starting point, random quantum fluctuations create small pockets of lower entropy, and crucially, not just one pocket, but two, growing outward in opposite directions. Picture a puddle of water resting on a perfectly flat table, sitting in still equilibrium. Now imagine tilting that table in 2 directions at once. Water would flow both ways simultaneously, forming 2 separate streams heading in opposite paths. Carroll and Chen's model proposes that the universe behaves exactly like that. From the equilibrium point, 2 branches emerge. In one branch, entropy increases in what its inhabitants would call the forward direction. That branch is presumably ours, our arrow, our sense of a future stretching ahead. In the other branch, entropy increases in the opposite direction. Anyone living inside that other branch would experience their arrow running the reverse way relative to ours. Their past would be our future. Their memories would build in what we would call backward, and none of it would feel unusual to them, because from the inside, and undeniable as ours feels to us right now, neither branch is the real one in some cosmic sense. Neither direction is the true direction. Both are local. Both are, in a strange sense, accidents of position. You experience time moving forward, not because the universe itself has an inherent forward direction baked into its structure, but because you happen to be standing inside one particular arm of a structure that has to. If that is correct, the arrow of time stops being a law of nature and becomes something closer to a point of view. The perspective you get from where you happen to be standing inside a much larger, symmetric structure, so the direction of time may be local. An accident of position rather than a cosmic law. But surely one thing remains untouched by all of this, right now. This exact moment, the one you are experiencing as you take in these words, feels like the one truly solid foothold left. You are here. You are now. Whatever time turns out to be, whatever direction it points, this present instant is undeniably real, except it is not nearly as solid as it feels. Return to that same 1905 paper by Einstein, the one that quietly demolished Aristotle's definition of time. Most people remember it for the equation relating energy and mass. But buried in the same paper is a discovery about simultaneity that turns out to matter even more for this story. Two events that happen at exactly the same moment for you do not necessarily happen at the same moment for someone else who is moving relative to you. This is not a trick of perception, not a delay caused by light taking time to travel, not something that better instruments could fix. It is a fact about the structure of the universe itself. Picture two bolts of lightning striking simultaneously. One hitting a tree to your left, one hitting a tree to your right. Standing exactly between them, you see both flashes arrive at your eyes at the same instant, so for you, they are simultaneous. Now picture someone riding past you on a fast-moving train. That person sees the same two lightning strikes, but because the train is moving toward one bolt and away from the other, the light from each bolt reaches the moving passenger at slightly different times. For that passenger, one bolt struck first and the other struck second. The two events were not simultaneous at all. From their point of view, here is the part that unsettles people the moment they truly absorb it. Neither of you is wrong. There is no experiment either of you could run to prove your version of now is the correct one. There is no hidden universal clock ticking away somewhere above the universe, silently recording the one true order of events. Your present moment belongs to you. The passenger's present moment is genuinely different, and both are equally valid, equally real, with no physical law anywhere that favors one over the other. The present moment, it turns out, is not a fixed feature stitched into the universe. It is a feature of your own velocity. Change your speed, and you change your now. The thing that felt like the single most solid piece of ground you could ever stand on, this instant, right here, depends on nothing more exotic than how fast you happen to be moving through space. If there is no single universal now shared by everyone everywhere, what does the entire universe look like to something that could somehow view all of it at once, from outside any one observer's particular vantage point? 3 years after Einstein's paper, in 1908, a mathematician named Hermann Minkowski, who had once been one of Einstein's own teachers, stood up in front of an audience in the German city of Cologne and delivered a lecture that reshaped how physicists think about reality itself. Minkowski had absorbed the mathematics of special relativity more deeply than almost anyone alive, and he realized something Einstein had not yet fully articulated. Space and time are not two separate things that merely interact. They are a single four-dimensional structure, often called a block. Minkowski put it directly, declaring that from that point forward, space by itself and time by itself were destined to fade into mere shadows. with only a union of the two, preserving an independent reality. Think about what it actually means for something to exist as a block. A city exists all at once. The neighborhood on the north side does not stop existing just because you happen to be standing on the south side at this moment. The streets you walked through yesterday are still there. The streets you will walk through tomorrow are already there, physically, structurally, waiting. You would never seriously believe the city is being newly created in front of you as you walk, and then erased behind you the instant you leave. The city simply is, in its entirety, all at once. Minkowski's block universe makes the identical claim about time. Your birth exists inside the block. Your death exists inside the block. This very moment you are experiencing right now exists inside the block, alongside every moment that came before it and every moment that will come after it. All equally real, none of them more genuinely present than any other. The sensation that you are moving through time, that the past has vanished and the future has not yet arrived, is not a property of the block itself. It is a property of you, specifically. You are something like a line drawn through a four-dimensional object, and being embedded inside that object means you experience your own line one point at a time, which is simply what it feels like to be a conscious slice moving through a structure that, from the outside, does not move, does not flow, and does not tick at all. It simply sits there, complete, finished, the way every page of an already printed and bound book exists at once, whether or not you have reached that page yet. You are not writing the story as you go. You are reading a story that was already finished before you opened the first page. That could sound like pure philosophy, an elegant mathematical picture with no bearing on physical reality. Except physicists eventually stopped arguing about it and went out and measured it directly. In 1971, two researchers named Joseph Haffel and Richard Keating decided to settle the question experimentally. Their setup was almost comically simple. They took for extremely precise cesium atomic clocks and loaded them onto ordinary commercial passenger jets, the kind anyone might book a seat on. Two flights circled the globe, traveling eastward in the same direction as the Earth's rotation. Two more circled westward against the rotation. A fifth matched set of clocks stayed put on the ground at the United States Naval Observatory in Washington. When the flights landed days later, the airborne clocks were compared against the stationary ones. The clocks that had flown eastward had fallen behind the ground clocks by roughly 59 nanoseconds. The clocks that had flown westward had gained roughly 273 nanoseconds. These were not rough approximations. The measured differences matched the combined predictions of special and general relativity to within the margin of experimental error. The clocks that traveled came home reading a genuinely different time than the clocks that had stayed still. Not because of any malfunction, not because of turbulence or temperature or cabin pressure, but because time itself passed at a measurably different rate for objects moving at different speeds and sitting at different altitudes. Those clocks came back from a slightly different version of the present, a fraction of a second removed from the now, that had continued unfolding on the ground. The size of the effect is tiny at ordinary airplane speeds, mere billionths of a second, far too small for a human being to ever notice directly. But it is not zero, and if the gap opens up even slightly at roughly 900 kilometers per hour, imagine what happens as speeds climb toward 90% of the speed of light. At that point, the gap stops being invisible and starts becoming years, then decades. The present moment is not universal. It is personal, dependent on your location and your velocity, and ordinary commercial jets carrying cargo in their overhead bins have already proven it. This is not confined to laboratories and thought experiments. Right now, 24 satellites orbit the Earth at an altitude of roughly 20,200 kilometers, moving at nearly 4 kilometers every second. Each one carries its own atomic clock, and each of those clocks ticks at a slightly different rate than the clock inside your phone. Two separate relativistic effects are working on those satellites simultaneously. General relativity says a clock sitting in weaker gravity runs faster. And because the satellites are much farther from the center of the Earth, gravity up there is weaker. So their clocks gain roughly 45 microseconds every day compared to a clock on the ground. Meanwhile, special relativity says a clock moving faster runs slower, and because the satellites are moving at such high speed, their clocks lose roughly 7 microseconds every day from that effect alone. Combine the two, and the net difference comes out to about 38 microseconds every single day. 30-8 millionths of a second sounds trivial, something you would never notice in daily life. But the entire global positioning system, the network your phone relies on every time you open a map, depends on those timestamps being accurate to an extraordinary degree. Your phone works by comparing signals from at least 4 satellites, each carrying a precise timestamp, and calculating your position from the tiny differences in when those signals arrive. If the satellite clocks were allowed to drift by 38 microseconds a day, the position calculation would drift right along with them, building up to an error of roughly 10 kilometers after a single day, 20 kilometers after 2 days, and within a week your phone might place you in an entirely different city. So engineers correct for it constantly. Every satellite clock is deliberately adjusted to account for the fact that time simply does not pass at the same rate up in orbit as it does down on the surface. Every timestamp broadcast from every satellite has been quietly modified to compensate for the difference between two separate versions of the present moment. Something like 2 billion people use this system every single day, trusting an app to tell them exactly where they are standing. And the entire arrangement only works because engineers built the relativistic gap between two different nows directly into the underlying code, so physics has taken apart the outside world piece by piece. Time has no working definition. Its direction turns out to be a statistical accident rather than a fundamental law. The present moment depends on your speed and your altitude rather than being shared universally. But there is still one place where time feels absolutely, undeniably real, inside your own head. Close your eyes right now and you can feel it, a current, a flow. The unmistakable sensation that this moment is happening and then it slips into the next one. Whatever the equations claim, whatever the satellites measure, you experience time passing. And that experience is the most immediate thing you have. In 1983, a neuroscientist named Benjamin Libet designed an experiment that cracked open the inside of the mind the same way Einstein had cracked open the outside world. The setup was straightforward. A person sits facing a clock with a single dot sweeping around its face, and they are told to flex their wrist whenever they feel the spontaneous urge to do so, with no schedule and no external cue. 3 separate things get measured. First, electrodes on the scalp detect the moment the brain's motor cortex begins preparing the movement. Second, the participant reports the exact position of the dot at the instant they felt themselves decide to move. Third, the actual physical movement of the wrist itself is recorded. Intuitively, the order should be obvious. You decide, your brain fires the signal, and then your wrist moves. Decision first, neural signal second, action third. That is the order it feels like from the inside, and that is the order most people would confidently report. DeWitt measured a different sequence entirely. The electrical signal in the motor cortex appeared roughly 350 milliseconds before the participant reported making the conscious decision to move. The brain had already begun preparing the action, before the conscious mind had any awareness that a decision was coming. In other words, your brain initiates the process, and only afterward does it inform you that you chose it. The sequence you consciously experience, the one where you decide and then your body responds, is not the actual sequence of events. It is a reconstruction, assembled after the fact and delivered to your awareness with a time stamp that has been quietly shifted backward to preserve the feeling that you were in charge the whole time. Perhaps that is a narrow, unusual case, limited to something as small as flexing a wrist. Surely the broader, more ordinary experience of time passing is more trustworthy. Starting in the early 2000s, a neuroscientist named David Eagleman began pulling on exactly that thread. And what he found is that the now you experience is not really a single unbroken moment at all. It is an edit. Your brain does not receive the world in one unified package. It receives fragments, arriving through completely different channels at completely different speeds. Light strikes your eyes, sound strikes your ears, pressure strikes your skin, and each of those signals travels to the brain along a different pathway at a different speed. Vision tends to be slower to process than sound. Touch depends heavily on where on your body the contact occurs. Since a tap on your nose reaches your brain faster than a tap on your toe, simply because the physical distance is shorter. These gaps are not trivial. Depending on the sense involved and the location on the body, they can range anywhere from roughly 80 to 500 milliseconds, which means half a second can separate the fastest incoming signal from the slowest, and yet you never notice a gap. You do not watch a glass shatter and then hear the crash half a second later as two disconnected events. You experience both together, seamlessly, in a single unified instant, because your brain deliberately waits. It gathers up the scattered fragments, holds back the ones that arrived early until the slower ones catch up, and only then stitches everything together into the single moment it hands over to your conscious awareness and labels the present. There is a well-documented glitch that exposes this stitching process directly, called chronostasis. Glance quickly at an analog clock, and the second hand can appear to freeze in place for a beat that lasts noticeably longer than a normal second, before resuming its regular ticking. What is actually happening is that while your eyes were moving toward the clock, they had no stable image to work with, so once your eyes settled, your brain grabbed the very first clear frame it received, the image of the second hand sitting still, and stretched that single frame backward in time to paper over the gap during which your eyes were in motion. You are not watching time unfold. You are watching your brain's reconstruction of time, assembled from disconnected pieces and stitched together along seams designed to stay invisible. In 2002, a researcher named Patrick Haggard at University College London ran a cleaner, more controlled version of this same idea. A participant presses a button, and precisely 250 milliseconds later, a tone sounds, a simple, direct cause followed by an equally simple effect. The participant is asked only to report exactly when each event happened, the button press and the tone. The answers came back systematically wrong, and wrong in the same direction every time. Every subject reported pressing the button slightly later than they had actually pressed it, and reported hearing the tone slightly earlier than it had actually played. The brain had pulled the two events toward each other in time, shrinking the gap between cause and effect, as though it needed the connection between them to feel tighter and more immediate than it really was. Haggard called this effect temporal binding. Your brain does not passively record the relationship between an action and its consequence. It actively edits that relationship, deciding that two events are causally linked, and then quietly adjusting their perceived timing to make the link feel stronger and more instantaneous than it actually is. Flip a light switch, and it feels as though the light comes on instantly. It does not. There is a real gap. Your brain simply closes that gap because a tight, immediate feeling connection between an action and its result is more useful for navigating the world than a perfectly accurate one would be. Scale that idea up, and every single time you feel that one event caused another, you are not detecting a genuine relationship out in the world. You are watching your own brain construct that relationship and paste it over the raw incoming data. The felt sense of cause leading smoothly into effect is not a discovery your senses are making. It is a production your brain is staging, cutting the footage after the fact to match a story it has already decided to tell. The order is fabricated. The duration is fabricated. Even the felt connection between cause and effect is fabricated. But perhaps the raw machinery generating all of this is still tethered to something objective and unchanging underneath. Your brain does have something like an internal clock, and it is not a metaphor. It is an actual measurable oscillation. Populations of neurons fire in coordinated rhythmic waves, and the rhythm most closely tied to conscious experience of time is called the gamma rhythm, cycling somewhere between roughly 30 and 100 times every second. That rhythm functions something like the refresh rate of your conscious experience, the pace at which your brain samples the surrounding world, assembles a coherent frame, and delivers that frame to you as the present moment. If that gamma rhythm were perfectly stable, you could reasonably argue that at least the raw hardware underlying your sense of time is anchored to something fixed and reliable, a kind of biological metronome. But it is not stable at all. In 2016, a research team led by the neuroscientist Enzo Tagliazucchi published findings on what happens to the gamma rhythm under the influence of substances that significantly alter brain chemistry. The rhythm fractures. The normally synchronized firing patterns that hold your experience of time together scatter apart, with some brain regions speeding up and others slowing down, and the unified sense of a single present moment dissolves along with it. The subjective sense of duration changes correspondingly, with seconds sometimes stretching into what feels like minutes, or minutes seeming to collapse into almost nothing. Long-term meditation practice appears to produce related, if gentler, effects, with studies showing that experienced practitioners exhibit measurably different gamma patterns and correspondingly altered senses of duration, time feeling slower, faster, or oddly both, depending on the depth of the practice. Extreme stress and trauma do something similar without any chemical or meditative intervention at all. People who survive car accidents or sudden falls routinely report that time seemed to slow down dramatically, that a 3-second event felt like it lasted 30 seconds, packed with far more sensory detail than an ordinary moment. A surge of adrenaline appears to spike the brain's effective sampling rate, generating more subjective frames per second, so that each second, subjectively, stretches out and feels longer. Your experience of time, in other words, is not wired directly to the external universe. It is wired to an internal electrical frequency generated by tissue inside your own skull. a frequency that can be bent by chemistry, reshaped by sustained practice, and overridden entirely by a sharp enough jolt of fear. Speed that internal rhythm up, and the world around you seems to slow down. Slow it down, and the world seems to race ahead. Two completely independent lines of investigation have now arrived at the same unsettling conclusion from opposite directions. Physics examined time from the outside and found that it is not fundamental. Neuroscience examined time from the inside and found that it is constructed. The outside and the inside agree with each other, which raises an obvious question. Is there a level deeper than both of these? A level beneath physics and beneath the brain, where time might finally turn out to be real after all? That deeper level is the quantum level, the bottom beneath the bottom. If time is real anywhere in this universe, it should show up there. In 1978, John Archibald Wheeler, the same physicist whose best attempt at a definition of time had been a joke, proposed a thought experiment that would eventually be built for real. He called it the delayed choice experiment. The setup relies on one of the most basic pieces of equipment in quantum optics, a beam splitter. Fire a single photon at it, and the splitter offers the photon two possible paths, left or right. Place detectors at the end of each path, and you find out definitively which path the photon actually took, behaving like a discrete particle traveling one single route. But instead, place mirrors that redirect both paths so they cross again, and position a second beam splitter at that crossing point, and something changes entirely. The photon interferes with itself, producing a pattern that could only arise if the photon had somehow traveled both paths simultaneously, behaving like a wave rather than a particle. This much was already standard, well-established quantum mechanics. The unsettling twist Wheeler added was this: what if the decision to insert or remove that second beam splitter is made only after the photon has already entered the apparatus and is already in transit? If the second splitter goes in, the photon behaves as though it took both paths. If it stays out, the photon behaves as though it took only one. The photon's past behavior would then appear to depend on a decision that had not even been made yet at the time that behavior occurred. Wheeler proposed this purely as a thought experiment in 1978. In 2007, a research team led by Vincent Jacques at the École Normale Supérieure in Paris actually built it, using real single photons, real beam splitters, and real detectors, with the choice of whether to insert the second splitter made by a genuine random number generator only after each photon had already passed the first splitter. The results matched Wheeler's prediction exactly. When the second splitter was inserted, the data showed the photon had effectively traveled both paths. When it was removed, the data showed the photon had traveled only one. The decision made after the photon had entered the apparatus determined, not merely influenced, what the photon appeared to have done before that decision was ever made. The experiment has since been reproduced many times in laboratories around the world, and no model relying on some hidden, unmeasured variable has managed to survive the accumulated data on the deepest physical level currently accessible to experiment. The ordering of before and after is not fixed in the way everyday intuition assumes. A related and even more fundamental result comes from a theorem proved in 1964 by a physicist at CERN named John Bell's theorem asks whether the strange behavior of entangled quantum particles could be explained by some hidden mechanism we simply have not discovered yet, some deeper layer of reality where causes still come cleanly before effects, and nothing travels faster than ordinary signals allow. Bell proved mathematically that the answer is no. There is no such hidden layer waiting to be found. The strangeness is not a temporary gap in human knowledge. It is simply how reality behaves at that level. In 1982, a French physicist named Alain Aspect put this to an experimental test. He took pairs of entangled photons, sent them flying off in opposite directions, and measured a particular property of each one. The results correlated perfectly every single time, in a way stronger than any prearranged agreement between the two photons could possibly account for. Bell's theorem rules out the tempting explanation that the photons simply agreed on their answers in advance. The way two coins flipped from the same hand might land in a coordinated pattern. The only way to reproduce the correlations Aspect actually measured is if the two photons remain connected in some sense that does not involve any signal, force, or wave crossing the space between them at all. Nothing physically travels from one to the other. The correlation simply exists instantaneously across any distance. Einstein, who spent much of his later career convinced that quantum mechanics must be incomplete, famously dismissed this as spooky action at a distance. In 2022, the Nobel Prize in Physics was jointly awarded to Alain Aspect, John Closer, and Anton Zeilinger for experiments that settled the question permanently. The correlations are real, and they do not travel through space or through time at all. Two particles separated by an entire galaxy would respond to each other with no elapsed moment between the responses. Not merely faster than light, which would still technically be inside the framework of time, but genuinely outside of time altogether. The connection simply does not use time as part of its mechanism. If entanglement genuinely does not require time to operate, then the natural question flips around entirely. Maybe it is not that time contains entanglement. Maybe time itself needs entanglement in order to exist. In 2013, two of the most cited theoretical physicists alive, Juan Maldacena and Leonard Susskind, published a conjecture built around exactly that flip. One that connects two of Einstein's own papers from 19th, written with different collaborators and considered, for roughly 78 years, to be describing entirely unrelated physics. One of those papers, with Nathan Rosen, described bridges connecting distant points in spacetime, structures now commonly known as worlds. The other, with Boris Podolsky and Nathan Rosen, described quantum entanglement itself, particles connected across distance with no signal passing between them. Maldacena and Susskind proposed that these are, in fact, the same underlying phenomenon seen from two different angles. Every entangled pair of particles, in this view, is connected by something equivalent to a wormhole, and every wormhole is a manifestation of entanglement. The bridge and the connection are simply one object viewed from two different mathematical perspectives. Follow that logic all the way through, and something remarkable falls out. If entanglement and the geometry of spacetime really are the same thing, then spacetime is not a pre-existing container that quantum connections happen to sit inside. Spacetime is built out of those quantum connections. Remove the entanglement, and the stage it was supposedly sitting on disappears along with it. What remains is a web of pure correlations, and only when enough of those correlations accumulate and are viewed from far enough away do they begin to resemble something like distance, duration, and cause and effect. Under this picture, time does not produce entanglement. Entanglement produces time. The thing that looked like the foundation turns out to be the product, and the thing that looked like the product turns out to be the actual foundation. And these are not fringe ideas scribbled in a basement somewhere. They sit at the very center of modern theoretical physics, and no one has yet managed to prove them wrong. If time really is built out of entanglement in this way, there ought to be a concrete mechanism showing precisely how the felt experience of time can emerge from a system that fundamentally does not contain time at all. In 1983, two physicists named Don Page and William Wouters proposed exactly such a mechanism, one so elegant it almost feels like a magic trick. Treat the entire universe as a single closed system with nothing existing outside it at all. No external clock ticking away on some cosmic wall keeping track of the seconds from an outside vantage point. In quantum mechanics, a fully closed system that contains literally everything is described by one single, unchanging overall state. That state cannot change, because change would require something to be different from one moment to the next, and any such comparison requires a reference point outside the system, and by definition there is no outside. The universe as a whole, under this description, is entirely static. Not frozen in time exactly, since even the concept of frozen implies time passing around it. There is simply no time available for it to be frozen in. Now split that total system conceptually into two pieces. Call one piece the clock, and call the other piece everything else. Let the clock, in effect, observe the rest of the universe. The quantum correlations between these two pieces, the way their internal states become tangled together, start to look from the clock's own internal perspective, exactly like ordinary evolution through time. The clock registers a before, it registers an after. It measures a gap between the two. From inside that subsystem, time genuinely appears to exist. From outside, looking at the whole closed system together, there is none at all. In 2013, a research team led by Ekaterina Mareva at the National Institute of Meteorological Research in Turin, Italy, actually built a physical version of this setup using pairs of entangled photons. An observer positioned entirely outside the entangled pair, measuring the whole system from outside, detected no change, no sequence, and no duration whatsoever, as though nothing had happened at all. An observer who was themselves entangled with one of the two photons, measuring the other, detected change, sequence, and duration. In other words, time playing out normally. Same photons, same laboratory, same physical apparatus, and yet two entirely different realities depending on where the observer happened to stand relative to the system. And notice something important about that setup. You, right now, have never once stood outside. You are always embedded somewhere inside the system you are trying to measure, tangled into everything around you, a part of the universe attempting to look at another part of itself. The gap you casually call a second, the flow you casually call the present moment, may not be the universe itself moving forward. It may simply be what it looks like when one small fragment of a much larger structure tries to measure the whole from inside, and mistakes that internal measurement for a river flowing past. In 19, a physicist named Bryce DeWitt wrote down an equation that fit on a single line and yet was meant to describe absolutely everything. The entire universe at once, every particle, every field, every force, every galaxy, every photon, every atom in your body, all wrapped together into one quantum mechanical expression. DeWitt was completing a line of thought that Wheeler himself had been circling for years. The underlying question was straightforward. We already have quantum mechanics, which describes very small things extraordinarily well. We already have general relativity, which describes very large things extraordinarily well. What happens when you try to write a quantum equation for the single largest thing that exists, the universe itself? The result became known as the Wheeler-DeWitt equation, and the result has a very specific problem. There is no variable representing time anywhere in it. Not because DeWitt overlooked it, not because he simplified the mathematics for convenience, not because he chose some shorthand notation. When you attempt to write quantum mechanics for a fully closed system that contains absolutely everything, the mathematics simply does not produce a time variable at all. It is not hidden somewhere inside another term waiting to be extracted. It is genuinely absent. The equation describes a universe in which nothing happens, and not in the sense of things happening very slowly or time being difficult to detect. In the sense that the very concept of happening does not apply at that level. Everything simply is, all at once, permanently. This has come to be known as the problem of time in quantum gravity, and it has remained unresolved since 1960. It is not a minor footnote that theorists occasionally debate at conferences and then set aside. It stands as the central obstacle blocking the unification of the two greatest theories in modern physics. General relativity absolutely requires time to function, since time bends, stretches, and tells matter how to move. Quantum mechanics, once applied to the universe as a whole, appears to erase time entirely, producing a description in which the very word when carries no meaning. Two theories, each confirmed to extraordinary precision, and one requires time while the other says it does not exist. For roughly 57 years, nobody has figured out how to reconcile the two. Someone did eventually take that absence seriously rather than walking past it. In 2004, a physicist named Carlo Rovelli published an essay carrying a title that likely made several of his colleagues wince. To blunt words, an instruction rather than a hypothesis. Rovelli is not writing from the sidelines. He is one of the founders of loop quantum gravity, one of the leading candidate theories attempting to unify general relativity with quantum mechanics, and he has spent his entire career working at the deepest level of physical reality currently accessible. His conclusion, after decades of that work, is that time simply is not a feature of that deepest level. His argument runs roughly like this. If you have complete information about a system, meaning you know the exact state of every particle and every field involved, you do not actually need time at all to describe it. You can describe the whole thing purely as a network of relationships between variables. This quantity correlated with that quantity. This state connected to that state, with no need for a before or an after. Just a web of relations existing together. Time, in Rovelli's view, only enters the picture once you lack complete information. Once some microscopic detail of the system is unknown to you and you are forced to fall back on a statistical description instead. Inside that statistical description, a parameter shows up that behaves the way time behaves, increasing steadily, giving you a direction, letting you talk sensibly about change and sequence and duration. But that parameter is not fundamental. It is a consequence of your own ignorance about the underlying details. Rovelli expanded this argument into a book published in 2017 called The Order of Time, translated into roughly 40 languages and selling millions of copies worldwide. The argument is not tucked away in an obscure academic journal. It sits openly on bookstore shelves everywhere. Time, in this view, is what appears whenever you do not know enough to see the fine-grained structure underneath. It is the blur you perceive when your vision is not sharp enough to resolve the individual threads. Sharpen that vision enough, gain complete knowledge of the underlying system, and the blur along with time itself, disappears. Rovelli removed time from the picture, but he left something behind: change. Relationships between variables can still shift. Correlations can still exist. A web can still have internal structure, even without any clock ticking above it to measure that structure unfolding. A physicist named Julian Barbour looked at exactly what Rovelli had left standing and decided to remove that as well. In 1999, Barbour published a book called The End of Time, and the title is not a metaphor. He means it entirely literally. Barbour's proposal is that the universe is not a sequence of events unfolding one after another at all. It is instead an enormous collection of configurations, each one a complete, self-contained arrangement of every particle in the universe, a single frozen frame containing everything: the position of every atom, the state of every field, the shape of every galaxy. In Barbour's model, these countless configurations do not follow one after another in any order. There is no designated first frame, second frame, or third frame. There is no sequence and no progression whatsoever. Only a vast space containing every possible configuration. A space Barbour calls Platonia. Every conceivable arrangement of the universe exists somewhere within Platonia, including the configuration in which you are reading this exact sentence, the configuration in which you stopped reading 5 minutes ago, and even the configuration in which you were never born at all. None of these configurations is more real than any other. None comes before or after any other. Here is the part that is genuinely difficult to sit with. Some configurations happen to contain structures that look exactly like records of a past. A brain full of vivid memories, a fossil embedded in rock, a photograph resting on a shelf, starlight that appears to have been traveling for 1,000,000 years. These structures exist entirely within their own single configuration. They are simply part of that one snapshot. And your own brain, which is itself just another part of that same snapshot, examines these apparent records and concludes there must have been a genuine sequence of events leading up to this moment. But according to Barbour, there was no such sequence. There is no film reel, and there is no projector running it. There are only photographs, and some of those photographs happen to contain images of what look like projectors inside them. Your memories, in this view, are not recordings of events that actually occurred one after another. They are simply structural features of the single frozen configuration you currently exist within. The sensation that time passed, that yesterday genuinely happened, that you were once a small child, is not a report arriving from an actual past. It is a pattern embedded inside one static, timeless frame. Not everyone accepted this quietly. In 2013, a physicist named Lee Smolin published a book called Time Reborn. Its title functioning as a direct rebuttal to Barbour. Where Barbour declared time dead, Smolin insists time is the single thing that was ever genuinely alive. Smolin is not a minor voice in the field either. He co-founded the Perimeter Institute for Theoretical Physics, one of the most influential research centers in the world, and has spent decades working directly on quantum gravity. His conclusion runs completely opposite to both Rovelli's and Barbour's. Time, in his view, is not an illusion, not a side effect of missing information, and not merely a pattern frozen inside an unchanging photograph. Time is real, more than real. It is, in fact, the only thing that is genuinely real. Smolin's argument runs like this: the laws of physics are not eternal, fixed truths written permanently into the fabric of existence from the very beginning. They evolve. They change over cosmic history. The speed of light the charge carried by an electron, the strength of the gravitational constant. All of it, in his view, is ultimately temporary, describing the universe only as it happens to exist right now, in this particular era. Those constants were different before, and they will be different again. What persists unchanged through all of that ongoing change is time itself. Time functions as the container, and everything else, every law and every constant, functions as shifting contents inside that container. Consider what each of these three positions costs you, because none of them lets your intuitive picture of reality stay fully intact. If Rovelli is correct, and time is fundamentally an illusion born of ignorance, then the laws of physics themselves sit fixed and eternal inside timeless equations, beautiful and permanent, but you personally lose time. You lose any real sense of moving through the world at all, and you become, instead, something closer to a stationary thread, woven into a web of relations that your own brain simply mistakes for a flowing river. If Barbour is correct, you lose not only time but motion and change as well, reduced to a pattern living inside a single still photograph that happens to contain the illusion of its own projector. If Smolin is correct, time survives fully intact. But the price is that the laws of physics themselves become temporary rather than permanent. The constants stop being constant, and the very foundation every equation in physics has ever been built on turns out to be shifting slowly underneath your feet even as you stand on it. 3 of the most respected physicists currently working in the field. 3 mutually incompatible answers to the exact same question. There is no door in this particular hallway that opens onto solid, unchanging ground. Every door available opens onto a different kind of fall so far. All of this has remained comfortably theoretical, equations on chalkboards, arguments exchanged in books, positions defended in public lectures. It would be reasonable to conclude that these are simply competing models, elegant on paper, while the real physical universe made of rock and starlight and ordinary light keeps working the way it always seemingly has. Except there are actual places within the real universe where time demonstrably stops functioning in the ordinary way altogether. In 1916, barely a year after Einstein published his general theory of relativity, a German physicist named Carl Schwarzschild solved Einstein's equations for the case of a perfectly spherical mass, doing the work from the trenches of the First World War and mailing his solution back to Einstein from the Russian front. What his solution described sounded, at the time, almost absurd. Compress enough mass into a small enough volume, and the surrounding geometry of space-time curves so sharply that nothing at all can escape it. Not matter, not light, not even information itself. The boundary beyond which escape becomes physically impossible is called the event horizon. Consider what happens to time right at that boundary. Picture someone falling toward a black hole while you watch safely from a great distance. As that person approaches the horizon, their clock appears, from your perspective, to slow down. Their movements grow visibly sluggish. Light coming from their body shifts steadily toward red, then deep red, then infrared, then nothing at all. They appear dimmer and slower the closer they get, and from where you are standing, they never actually seem to cross the line. Their clock approaches 0, and, from your vantage point, never quite reaches it. They appear frozen at the boundary, seemingly forever. Now switch entirely to their own perspective. They feel nothing unusual as they reach the horizon. No barrier, no wall, no sign that anything has changed at all. They cross it instantly, from their own point of view and continue falling onward. Their own clock ticks completely normally. Their heart beats normally. They notice no boundary whatsoever. Two observers, one watching a person appear frozen at the edge of time forever, and the other feeling absolutely nothing unusual while falling straight through, and both are correct. Neither is experiencing some kind of illusion. The universe simply does not choose one version over the other. It runs both simultaneously. Time is not merely slowing down at the horizon in some ordinary sense. Time is splitting into two separate realities that will never again agree with each other. What waits beyond the horizon is stranger still. Inside a black hole, the mathematics of general relativity does something that looks like an error but is not one at all. The roles ordinarily played by space and time effectively switch places. Outside the horizon, you can move freely through space, choosing your direction, left or right, up or down. But you cannot move freely through time. You can only move forward. And that is the one direction you are never able to reverse. Inside the horizon, that arrangement flips. The radial direction, the direction pointing toward the center, becomes the new time-like direction, and the ordinary time direction becomes space-like instead. What that means, in practice, is that falling toward the center is no longer a simple movement through space. It becomes a movement through time. And just as you cannot stop moving forward through ordinary time while outside the horizon, you cannot stop falling toward the center once you are inside it. Nothing is physically pulling you there. You are moving through time, and the center happens to be where time itself is heading. In 1965, Roger Penrose proved that this process has a definite endpoint. His singularity theorem, work that ultimately earned him a share of the Nobel Prize in 2020, demonstrated that under quite general conditions, gravitational collapse inevitably leads to a singularity, a point where the curvature of space-time becomes infinite, where density becomes infinite, and where every known physical law simply returns an answer of infinity, which in mathematics is essentially a polite way of saying the equations have broken down entirely. The description fails at that point. The sentence simply ends. At the singularity itself, time does not gradually slow to a stop. Time ceases to be a meaningful concept altogether. There is no moment after the singularity, because the very word after presupposes time, and time is precisely the thing that has just run out. You are not falling toward a location in space. You are falling toward the edge of the very last moment, the final tick, the point where the clock does not simply stop but ceases to exist as a concept at all. In 1974, a young physicist named Stephen Hawking discovered something entirely unexpected about black holes. They are not permanent fixtures of the universe. They evaporate. Hawking showed that the event horizon is not a perfectly clean boundary at the quantum level. Pairs of particles are constantly popping into existence and immediately annihilating each other throughout empty space everywhere in the universe, an entirely ordinary quantum phenomenon. But right at the edge of a black hole's horizon, something different can happen. A particle pair appears exactly at the boundary. One particle falls inward while the other escapes outward, carrying a small amount of energy away from the black hole with it. Over an unimaginably long stretch of time, the black hole gradually loses mass and eventually disappears entirely. A slow release now known as Hawking radiation. A black hole with roughly the mass of our Sun would take something on the order of 10 to the power of 67 years to fully evaporate this way. a span of time that dwarfs the current age of the universe by a factor that does not have an everyday name. But given enough time, the process does happen, and eventually, every black hole in the universe will be gone. This creates an enormous problem. Information about every object that ever fell into that black hole, every star, every planet, every beam of light, carrying detailed information about its structure, composition, and history, crossed the horizon and traveled toward the singularity where time itself ends. Once the black hole finishes evaporating, all that remains behind is a faint glow of thermal radiation with none of that original detailed information apparently preserved inside it. So where did the information actually go? If it was genuinely destroyed, that would violate one of the foundational principles of quantum mechanics, called unitarity, the rule stating that information is never truly lost, that every quantum process is, in principle, reversible, meaning you could always reconstruct the original input starting from the final output. If the black hole destroyed that information outright, this fundamental rule breaks, and the entire foundation of quantum theory cracks along with it. But if the information was not destroyed, it had to escape somehow, and the event horizon is explicitly a one-way boundary. Nothing is supposed to get out. So how does information leave a place from which nothing is able to leave? Hawking spent roughly 3 decades arguing publicly that the information really was destroyed, insisting that quantum mechanics itself would eventually have to bend to accommodate it. In 2004, he publicly reversed that position, conceding that the information likely does survive somehow, without ever fully explaining the mechanism by which it escapes. Nobody else has managed to explain it either. This puzzle, known as the black hole information paradox, has remained open for roughly 50 years, occupying some of the best minds in modern physics. Time itself ends inside the black hole. The object that once contained that time eventually evaporates away entirely, and yet the information that fell into it somehow does not disappear along with it. Time dies. Its contents apparently do not. Whatever a thing is, and whatever that thing once contained, turn out not to be the same, and nobody can yet explain exactly how that is possible. You might reasonably tell yourself that none of this affects you personally. Black holes are exotic, distant objects, theoretical curiosities sitting at the far edges of the universe, problems for professional physicists rather than for anyone else. Except in April of 2022, the Event Horizon Telescope collaboration released an actual photograph, not a computer simulation, not an artist's rendering, a genuine image of Sagittarius A star, the supermassive black hole sitting at the very center of our own Milky Way galaxy, with a mass roughly 4 million times that of our Sun, located about 26,000 light-years from wherever you happen to be sitting right now. That is not the far edge of the universe. That is the center of your own galaxy. Every star you have ever looked up and seen in the night sky is orbiting it. The Sun is orbiting it. The Earth is orbiting it. You yourself are orbiting it at this very moment, traveling at roughly 230 kilometers every second, completing one full lap around it approximately every 225 million years. The last time our solar system occupied this exact position in its orbit, dinosaurs had not yet appeared on Earth. The time before that, the most complex form of life on the planet was a simple fish, and sitting at the very center of that orbit, inside the object that everything you know is circling, time, according to the equations, equals exactly 0. Those same equations, The very same general relativity that corrects the clocks on GPS satellites and silently adjusts the time stamp on your phone every second of every day. Tell us that time comes to a genuine end at the center of Sagittarius A star, not inside a thought experiment, not inside a philosopher's hypothetical argument, but inside the identical mathematics that guides an ordinary car's navigation system to the nearest airport. You are gravitationally bound to an object where time, according to that mathematics, does not exist at all. And you have been orbiting it your entire life, along with every human being who has ever lived. The distance feels perfectly safe, 26,000 light years, but distance is only a measurement of space. And you are connected to that object not primarily through space, but through gravity. The very same force that bends time by 38 microseconds a day for a satellite in orbit, and bends time all the way down to zero at the center of the object your entire galaxy revolves around. The difference between the two is not a difference in kind. It is only a difference in degree. You are not especially far from the end of time. You are, in a very real sense, on a leash attached directly to it. A black hole is ultimately a single point, a local failure, a crack confined to one specific room in an otherwise intact structure. The natural next question is whether the entire floor is cracking, whether time faces some kind of limit, not just in isolated pockets, but across the universe as a whole. Back in 1852, a physicist named William Thomson, later known as Lord Kelvin, followed the second law of thermodynamics all the way to its ultimate conclusion. Entropy increases, disorder spreads, temperature differences flatten out. Hot objects cool and cold objects warm until every difference between them disappears entirely. This is the same arrow discussed earlier, the same underlying direction, but that arrow has a final destination. If entropy keeps increasing without limit, it eventually reaches a maximum, a point where there is nothing left to spread out, no temperature difference remaining to equalize, no gradient left to flatten, no usable energy remaining to do any work at all. The universe settles into complete thermodynamic equilibrium. Every point in space sitting at the exact same temperature, every particle carrying the exact same energy, with nothing flowing and nothing changing anywhere. Kelvin called this ultimate state the heat death of the universe. It is not a dramatic collapse or a violent explosion. It is, in a sense, the exact opposite. The moment the universe becomes so perfectly uniform that the very idea of a distinct moment stops having any meaningful content. Consider what that actually implies for time itself. If time is fundamentally the measure of change, as Aristotle first proposed, and if Boltzmann was correct that the direction of time is simply the direction of increasing entropy, then what happens once entropy has nowhere left to increase? There is no more change left to measure, no more direction left to point toward. The arrow has arrived at its final target, and there is nothing remaining on the other side of that target. Time does not stop at heat death in the sense of something grinding to a halt, because that would imply something is still present to be halted. Time simply empties out entirely. The word passing loses its meaning, because there is nothing left that could pass. The container remains in some technical sense, but the contents are gone. In 1998, two independent teams of astronomers pointed their telescopes at distant supernova and discovered something that, by all prior expectation, should not have been possible at all. The universe is not merely expanding. Its expansion is accelerating. Saul Perlmutter led one of the two research teams, while Brian Schmidt and Adam Rees led the other. and together they shared the Nobel Prize in 2011 for a discovery that fundamentally reshaped our picture of the future. Something is actively pushing galaxies apart from one another, and doing so at an ever-increasing rate. Physicists have taken to calling this force dark energy, which is really just a polite way of admitting nobody knows exactly what it is, though its effects are clearly observable. And its effect is to separate absolutely everything from everything else. The observable universe currently contains something on the order of 2 trillion galaxies, all of them visible, photographable, and measurable, and all of them steadily moving away from us, faster with each passing year, roughly 100 billion years from now. Every single galaxy outside our own local group, the small cluster containing the Milky Way, Andromeda, and a handful of smaller neighboring galaxies, will cross what is known as the cosmological horizon. Their recession speed will exceed the speed of light, not because those galaxies are physically moving through space faster than light itself, but because the space lying between us and them is stretching at a rate faster than light can ever cross it. Once a galaxy passes beyond our horizon, its light will never reach us again, not eventually, not with some future improved telescope, never. The photons it emits will travel toward us forever without arriving. Those galaxies will not explode and will not collapse. They will simply become invisible, permanently. The night sky will go dark, not all at once, but gradually, star by star and galaxy by galaxy. 100 billion years from now, an astronomer standing on whatever remains of Earth would look upward and see only the Milky Way, and nothing else at all, a single galaxy floating inside an otherwise empty void, with absolutely no remaining evidence that anything else was ever out there. The light will be gone. The records will be gone. The universe will resemble a single isolated island sitting inside an endless ocean. And no instrument and no theory will ever be able to prove that ocean once contained other islands. Under this picture, the universe will not end through some sudden collapse. It will end through forgetting. Everything that ever existed beyond our eventual reach will be erased from the observable record as thoroughly as if it had never happened at all, and time will still technically pass, but there will be nothing left for it to carry forward. The block universe picture, described earlier through Minkowski's work, makes this feel even stranger. If the four-dimensional block genuinely is the correct description of reality, then heat death is not something merely waiting for us somewhere off in the future. It is not an event scheduled to happen in 100 trillion years. It is a region, existing within the exact same overall structure that also contains the very moment you are experiencing right now. Picture a long road with you standing somewhere in the middle. To the east, the road stretches toward a distant city. To the west, it stretches toward an empty desert. Both the city and the desert already exist right now, in the present, even though you were standing somewhere between them. The city does not wink out of existence simply because you are not currently standing inside it, and the desert does not spring into existence only once you finally arrive there. Both were always there. The block universe claims exactly the same thing about time itself. The Big Bang is one region of the block. Your own life is another region. Heat death is yet another region. All of them are simply parts of the same single four-dimensional object, none of them more or less real than any other, and none of them is patiently waiting somewhere off in the distance for its turn to happen. The eventual death of the universe is not something that will someday happen to you at some future date. It already exists within the block, at exactly the same level of reality as this very sentence does. You are not slowly traveling toward it across some vast stretch of time. You are, in a strange but literal sense, already standing right next to it. The feeling that it lies far away is simply a property of your own particular position inside the block, and from a vantage point genuinely outside the block altogether. There would be no distance separating now from the end at all, no between of any kind. Beginning and end would appear as neighboring regions of one single object. The way the very first page and the very last page of an already completed, already bound book both exist simultaneously. You are not reading your way toward that final page. It has already been written. It is already bound into the book. It already exists, right now, with precisely the same certainty as the page you currently happen to be on in 2010. Roger Penrose proposed that this apparent ending might not actually be a true ending after all. Not because something new comes afterward in any ordinary sense, but because the ending and the beginning might turn out to be, in a very deep sense, the exact same event. He called the theory conformal cyclic cosmology. The underlying logic runs like this. In the extremely far future, the universe reaches full heat death. All ordinary matter has decayed away. All black holes have long since evaporated. The only things remaining are massless particles, namely photons. And a photon carries a genuinely strange property. It does not experience time passing at all. This is not a poetic metaphor. Within special relativity, any particle traveling at the speed of light has what is called a proper time of exactly zero. Its own internal clock, in effect, never ticks. It does not age. It does not experience any duration between being emitted and being absorbed. For a photon, those two moments are, in a real physical sense, identical. A universe composed entirely of photons, then, is a universe in which not a single particle carries a working clock. And if nothing in that universe has a clock, the universe correspondingly loses any way to measure scale at all. Distance becomes meaningless. Size becomes meaningless. The distinction between something enormously large and something vanishingly small simply disappears. Penrose realized that in exactly this state, an infinitely expanded, maximally cold universe becomes mathematically identical to an infinitely compressed, maximally hot point. The relevant numbers match. The geometry matches. The description is the same either way. The heat death of one cosmic era becomes, mathematically, the Big Bang that launches the next one, not as a loose metaphor, but as a genuine conformal equivalence. The transition requires no additional energy, no external mechanism, and crucially, no time at all. Because time is precisely the concept that has just lost all meaning at that point. One era simply fades away, and the next era emerges, with no true boundary separating the two. Because any boundary would require some notion of scale to define it, and scale is exactly what has vanished. The signal photon has already struck the screen. The data describing it has already been permanently written down. Nothing about the screen itself physically changes after the fact. And yet, when researchers sort through the signal photon's already recorded data, according to what was later decided about its entangled idler partner, the interference pattern is either present within that data or it is not, depending on a choice made afterward. The past itself did not change after the fact. Something even stranger appears to have happened instead. The past apparently contained both possible outcomes simultaneously all along. with the interference pattern and its absence both somehow embedded together within the original data from the very beginning. And the later choice simply determined which version turned out to be the real one. The past, under this interpretation, is not a single, fixed, settled record. It behaves instead like a superposition of multiple possible records, with the future acting as the mechanism that collapses that superposition down into one definite version: causality. Under this framework, no longer resembles a simple line running from yesterday toward tomorrow. It resembles something closer to a web, in which tomorrow genuinely reaches backward into yesterday and helps select which particular yesterday actually occurred. Both of these experiments break the ordinary ordering between two connected events, where event A precedes event B, yet B still somehow determines A. That alone is strange enough. But in 2017, a research team led by Julia Rubino at the University of Vienna carried out an experiment that removes the concept of ordering entirely. It is known as a quantum switch experiment. The setup involves two separate quantum operations, conveniently labeled A and B under ordinary classical physics. Either A happens before B, or B happens before A. One or the other, always. Even in cases where you personally do not happen to know which order occurred. Rubino's team placed the controlling system into a genuine quantum superposition, and the measured result showed that operation A effectively happened before B and after B at the very same time. Not one or the other, but genuinely both at once. The causal order between the two operations was itself placed into quantum superposition. This is not merely a matter of interpretation or philosophical framing. The experiment produces a directly measurable physical result. When the causal order is held in superposition this way, the system achieves a computational advantage that is fundamentally impossible to reproduce under any single fixed ordering of A and B. You cannot replicate the same result by simply running A first, and then B. You cannot replicate it by running B first and then A. You cannot replicate it by flipping a coin and randomly choosing one order or the other beforehand. The advantage exists only when the ordering itself remains genuinely undefined. The experiment has since been reproduced across multiple laboratories with consistent results throughout. The causal order connecting to physical events is apparently not a simple settled fact about the universe. It behaves instead as a genuine quantum variable, one that can be placed into superposition in exactly the same way a photon's position or polarization can be. Before and after are not fixed, built-in properties of reality after all. They function instead as measurable observables, whose values depend on how and when you choose to measure them. At the deepest currently accessible level of physics, the plain statement event A happened before event B does not carry a definite truth value until some specific measurement forces it to settle on one particular answer. Time, followed all the way down through this chain of results, keeps spiraling further away from anything solid. It has no working definition. Its direction turns out to be a statistical accident rather than a fundamental rule. The present moment turns out to be personal rather than universal. Your own brain actively fabricates the felt sense of flow. Quantum mechanics appears to break ordinary causality outright. The most successful equations physics has ever produced simply erase the time variable when applied to the universe as a whole. Black holes bring time to a literal, physical end. The universe itself appears to be heading toward a state in which time eventually empties out entirely. And now, Direct laboratory experiments show that the future can determine the past, and that the causal order connecting to events is itself a quantum variable rather than a settled fact. All of that evidence points in essentially the same direction. Time is not fundamental, but there is one experimental result that appears to point the other way, if only barely. In 2019, the LHCb detector at the Large Hadron Collider at CERN observed a process in which the ordinary symmetry between forward and backward time is genuinely broken. The process involves the decay of particles called d-mesons, composed of a charm quark paired with an up anti. When these particular particles decay, the resulting process does not look identical when you mathematically reverse the direction of time. The CPT theorem discussed earlier, the very same 1950s result, establishing that all fundamental physical laws remain symmetric under a combined reversal of charge, parity, and time, also implies that any violation of charge parity symmetry is mathematically equivalent to a violation of time reversal symmetry itself. The LHCb results demonstrate a genuine asymmetry of this kind. At the level of fundamental physical law, time does appear to have a preferred direction, at least in this one specific context. But the actual magnitude of that asymmetry matters enormously here. It shows up in exactly one particular type of decay, involving exactly one particular type of particle, and the size of the effect amounts to only a small fraction of 1%. Every other known process in physics, every other particle, every other interaction ever studied, remains perfectly the everyday arrow of time you personally experience, the one responsible for cooling coffee, forming memories, and aging cells, has no demonstrated connection whatsoever to this tiny crack in the underlying symmetry of d-meson decay. The only place in the entirety of fundamental physics where time genuinely appears to have a built-in direction is confined to a fraction of a percent of a single decay process, and the overwhelming remainder of the universe stays completely silent on the question. The arrow of time you actually live inside has no explanation at the level of fundamental law. It only has an explanation at the level of statistics, and that statistical explanation ultimately rests on an assumption that nobody has ever been able to justify. This brings the story right back to where Boltzmann originally stood, except now the depth of the hole beneath his feet is far better understood than it was in his own lifetime. There is a clear underlying reason nobody has managed to answer this question definitively. The two theories describing the universe with the greatest precision physics has ever achieved fundamentally disagree about what time actually is. General relativity treats time as dynamic. It bends, it stretches, it slows down near massive objects, functioning as an active part of the fabric of space-time itself, a fabric shaped continuously by the matter and energy it contains. Time, under general relativity, is not a passive background. It is an active participant. Quantum mechanics treats time in exactly the opposite way. There, time functions as a fixed external parameter, sitting entirely outside the physical system being described. It does not bend. It does not respond to matter at all. It simply ticks forward at a constant, unchanging rate, providing a stable stage upon which quantum events play out. Both theories have been confirmed to an extraordinary degree of precision. General relativity correctly predicts the orbital behavior of Mercury, the bending of starlight around massive galaxies, and the overall expansion rate of the universe. Quantum mechanics correctly predicts the exact spectral lines of hydrogen, the detailed behavior of semiconductors, and even the existence of the Higgs boson. matching experimental results to something like 14 decimal places of accuracy. These stand as the two most successful theories in the entire history of science, and they simply cannot both be correct about the fundamental nature of time. Time cannot be simultaneously dynamic and fixed. It cannot be both an active part of the fabric of reality and something entirely external to that fabric at once. It cannot bend and also refuse to bend. In order to unify these two theories into a single coherent framework, physicists first have to settle, once and for all, what time actually is. That single, unresolved question is the core of what is known as the problem of quantum gravity. And it has remained open for roughly 90 years now. String theory attempted to solve it, and instead produced a landscape containing something on the order of 10 to the power of 500 possible mathematical solutions, with no clear way to determine which one, if any, describes our actual universe. Loop quantum gravity attempted to solve it by removing time altogether and replacing it with a discrete network of quantum states, but it has struggled to fully recover the smooth, continuous space-time described by general relativity at large scales. Causal dynamical triangulation attempted a solution. Causal set theory attempted a solution. 90 years have passed, spanning roughly 4 full generations of physicists. During that same span of time, science managed to split the atom, land human beings on the moon, sequence the complete human genome, directly detect gravitational waves rippling through space, and capture an actual photograph of a black hole. And across that same 90 years, essentially zero net progress has been made on the specific question of what time fundamentally is. Not slow, incremental progress, zero. And this disagreement is not confined to published papers and public lectures. There is a real difference between what a scientist writes for a general audience and what that same person says when asked, informally, how the problem actually feels to live with. Take Sean Carroll. Based at Caltech, one of the most widely cited cosmologists working today, and the host of a well-known science podcast, someone who has spent years translating quantum mechanics, general relativity, and entropy into language millions of people can follow. In a conversation in 2023 about the nature of time, he said plainly that we do not know whether time is fundamental, and that he was not confident we would know within the coming decades. That is not a fringe researcher hedging cautiously. That is one of the most prominent working physicists on the planet, stating, without qualification, that the question is genuinely stuck. Take Carlo Rovelli. In an interview in 2018, speaking not as a theorist defending a published position, but simply as a person answering honestly, he said that when he considers the genuine possibility that time does not exist, he feels a kind of vertigo, a physical vertigo. The same man who helped write the equations that removed time from quantum gravity admitted feeling dizzy at the thought that his own equations might actually be correct. Take Lee Smolin. In Time Reborn, in passages where he steps back from the technical mathematics and allows himself to simply reflect, he wrote that the question of the nature of time is the question everything else ultimately depends on. That whether we can understand the universe at all hinges on whether we can understand time, and that we currently do not understand it. 3 people who have gone further into this problem than almost anyone alive. 3 people who have spent decades working at the very edge of the field. And when you ask them not what they officially argue in print, but what they genuinely feel, the answer comes back the same each time. Vertigo, uncertainty, a kind of quiet unease. They are not hiding an answer from the rest of us. They are not sitting on some discovery. waiting for the perfect moment to reveal it. They are standing at the edge of a genuine cliff, and none of them can see the bottom. Everything laid out here is true as far as current physics and neuroscience can establish. Time has no working definition. Despite roughly 3,000 years of the most rigorous minds humanity has produced trying to construct one, its direction is not a fundamental law, but a consequence of a starting condition nobody can explain, propped up by a probability so vanishingly small that the number describing its unlikelihood does not fit inside the very universe it supposedly produced. The present moment does not exist as a fixed structural feature of reality. It depends on your speed and your altitude, and in a real sense it belongs only to you and to nobody else. Your own brain does not passively observe time passing. It manufactures the sensation, faking the order of events, faking their duration, faking the tight link between cause and effect, stitching it all together into what feels like a single, seamless flow while carefully hiding the seams. At the deepest level physics can currently access, the future appears to reach back and help determine the past, and the causal order between two events can itself be placed into quantum superposition. The best equations physics has ever produced describe the universe without any variable representing time at all. Black holes bring time to a literal end at a point our entire solar system quietly orbits once every roughly 225 million years, and the universe as a whole appears to be heading toward a state in which time, by their own admission, uncertain and unsettled, not because they are concealing something, but because they reached the place where solid ground was supposed to be, and instead found open air. That much is simply the honest state of things, and it is entirely reasonable for it to feel unsettling. A species capable of discovering that it cannot fully define the most basic feature of its own existence has earned the right to feel a little destabilized by that fact. But here is the part worth sitting with, a little longer than the vertigo itself. You are here, right now, whatever now ultimately turns out to mean. Whatever here ultimately turns out to mean, and whatever the word you ultimately refers to inside a four-dimensional block where, according to some physicists, every moment already exists simultaneously. Something in you is undeniably experiencing this. Something in you is turning these sentences into meaning as you go. And whatever that something is, it does not require a finished equation in order to exist. It does not require a completed definition. It does not need permission from theoretical physics in order to keep going. The question of what time actually is may never receive a final answer. The flaw beneath the arrow may never be found. The cliff these physicists are standing on may genuinely have no visible bottom. And none of that changes the fact that you are, right now, still standing, still breathing, still carrying things you want to accomplish, places you would like to go, and a version of yourself you are still in the process of becoming. None of that depends on this question ever being fully resolved. None of it is waiting patiently for physics to finish making up its mind. If any of this has been genuinely interesting to sit with, there is a lot more of this kind of territory worth exploring together. The places where physics stops offering easy answers and starts asking better questions instead. And it tends to be the kind of thing that rewards coming back to what research continues right now. Decades after Boltzmann, decades after Wheeler, decades after Rovelli, Barbour and Smolin first staked out their competing positions, physicists are still refining tests of the delayed choice and quantum iriser experiments, looking for any subtle deviation that might finally reveal a hidden layer beneath the strangeness. Cosmologists are still combing through data from the cosmic microwave background, searching for the faint circular imprints Penrose's cyclic model predicts, with new missions promising sharper data in the coming years. Theorists working on loop, quantum gravity, string theory, causal set theory, and causal dynamical triangulation continue refining their mathematics, each hoping to be the one framework that finally recovers a coherent picture of time from underneath the quantum description of the universe. None of them currently agree with each other, and that disagreement itself is worth paying attention to, because it means the question is still genuinely open, not settled and simply awaiting confirmation. What nobody currently knows is arguably more interesting than what everybody already agrees on. Nobody knows why the universe began in the specific configuration it did. Nobody knows how information genuinely escapes an evaporating black hole. Nobody knows whether Rovelli, Barbour, or Smolin is closer to correct, or whether all three turn out to be equally incomplete descriptions of something stranger than any of them proposed. Nobody knows whether Penrose's cyclic universe is a genuine description of reality or an elegant, mathematical curiosity that happens not to correspond to anything real. That open uncertainty is not a failure of physics. It is closer to a map of exactly where the genuinely interesting work still remains to be done, so the ground may never fully solidify beneath this particular question, and you can still choose to live fully inside whatever this present moment actually turns out to be. Chase the things that matter to you. Build whatever it is you are trying to build. Remember clearly who you are on the days when nobody else happens to be watching. And be gentle with yourself on the days when even the ground beneath your own feet starts to feel a little thin. The universe may not yet have handed anyone a finished answer to what time is. It has, at the very least, handed you this moment to spend however you choose.